the law talks about two types of changes: physical and chemical. Let's look at an experiment to verify the part about the physical changes. Let's place some ice cubes in a dish and weigh it. Let's say that the weight is X. If we heat the ice, it will melt and form water. If we weigh the water, we notice that the weight is the same as the weight of ice. This proves that when matter undergoes a physical change, like in this case, the total mass of the reactants is equal to the total mass of the products. Now, let's verify the part about chemical changes.
We'll fill sodium chloride and silver nitride in the two limbs of Landau's tube.
Now, let's seal both the limbs with a rubber cork.
Let's weigh the tube and note the weight. This is the weight of reactants before taking chemical reaction. Now, tilt the tube to mix the solutions thoroughly. Reaction takes place, and we notice that a white precipitate of silver chloride is formed in the tube along with sodium nitrate solution.
Let's weight the tube after the reaction. We observe that the weight remains the same. Thus, we can conclude that when matter undergoes a chemical reaction, the total mass of the reactants is equal to the total mass of the products.
That is, during any chemical reaction, matter is neither gained nor lost.
Hence, this law is also called the law of indestructibility of matter. Now let's look at the next law. Law of definite proportions. As the name suggests, this law deals with the composition of various elements present in a compound. In 1799, Joseph Proust proposed the law of definite proportions. This law states that a pure chemical compound always contains the same elements combined together in the same fixed ratio by mass. For example, the water we get from any source such as river, well, lake, sea, or from any other place always contains hydrogen and oxygen elements in the ratio of 1:8 by mass. Thus, we can say that a given compound always contains exactly the same elements in the same fixed proportion by mass. However, this law does not apply if an element exists in different isotopes, which may form a compound.
For example, if a carbon-12 isotope combines with oxygen to form carbon dioxide, the ratio of carbon to oxygen is 3:8. But if a carbon-14 isotope combines with oxygen, then the ratio of carbon to oxygen is 7:16. Another limitation of the law is that elements may combine in the same ratio, but the compounds formed may be different. For example, the compounds ethanol and dimethyl ether have the same number of carbon, hydrogen, and oxygen atoms, but their arrangement is different. That is, the compounds are different.
In 1804, Dalton proposed the law of multiple proportions. This law states that when two elements combine to form more than one chemical compound, then the masses of one of the elements that combine with the fixed mass of the other element bears a simple ratio. For example, when the elements carbon and oxygen combine, two compounds, namely carbon dioxide and carbon monoxide, can be formed.
As seen in the equation for carbon dioxide, 24 parts by mass of carbon combine with 32 parts by mass of oxygen.
Whereas, when carbon monoxide is formed, 12 parts by mass of carbon combine with 16 parts by mass of oxygen.
These masses of oxygen bear a simple ratio of 32:16 or 2:1. In these reactions, a fixed amount of carbon is combining with multiple proportions of oxygen to form carbon dioxide and carbon monoxide.
Similarly, when sulfur dioxide and sulfur trioxide are formed, the masses of oxygen bear a simple ratio of 32:48 or 2:3. In these reactions, a fixed amount of sulfur is combining with multiple proportions of oxygen to form sulfur dioxide and sulfur trioxide. In 1808, Gay-Lussac put forward a generalization which defines the relationship between volumes of gaseous reactants and products. This generalization is known as Gay-Lussac's law of combining volumes. It states that when gases combine or are produced under similar conditions of temperature and pressure, volumes of reacting gases as well as the products bear a simple ratio to one another.
For example, when one volume of hydrogen reacts with one volume of chlorine, the result is always 2 volumes of hydrogen chloride. Thus, ratio of volumes of reactants and products of this reaction is simple.
Another example is when 1 liter of nitrogen gas reacts with 3 liters of hydrogen gas to produce 2 liters of ammonia gas. Since all the reactants and products are gases, the mole ratio of nitrogen gas to hydrogen gas to ammonia gas is same as the ratio of the volume of each gas participating in the reaction. That is, 1:3:2. In 1811, Avogadro suggested that matter consists of 2 kinds of particles, namely atoms and molecules. He defined an atom as the smallest particle of an element, which can take part in a chemical reaction, and may or may not be capable of independent existence. A molecule is the smallest part of an element or compound which is capable of independent existence. He concluded that since the smallest particle of a gas, which can exist independently, is a molecule and not an atom, hence, the volume of gas must be related to the number of molecules. he proposed a law known as Avogadro's law, which states that under similar conditions of temperature and pressure, equal volume of all gases contains equal number of molecules. For example, 1 volume of hydrogen combines with 1 volume of chlorine to form 2 volumes of hydrogen chloride gas. For this to be true, it would mean that the number of molecules in 1 volume of hydrogen, N, will be equal to the number of molecules in 1 volume of chlorine, N. During the reaction, they will form 2 volumes of hydrogen chloride gas, which will contain N plus N, that is, 2N number of molecules, which means that the number of molecules in 1 volume of hydrogen chloride is equal to N. Thus, proving Avogadro's law. While scientists studied matter and formed the laws of chemical combination, they were unable to answer some questions. For example, why are 2 elements different, or why do elements combine to form compounds? Dalton studied the structure of matter, and in 1808, he proposed a theory to describe the structure of matter. This theory was named after him as Dalton's atomic theory. The theory states that matter consists of extremely small, indivisible and indestructible particles called atoms. Atoms of the same element are identical in shape, size, and mass. Atoms of different elements have different sizes, masses, and chemical properties. Atoms of 2 or more elements combine in a fixed ratio to form a compound. Atoms can neither be created nor be destroyed during a chemical reaction. Chemical reactions involve combination, separation, or rearrangement of atoms. Scientists used Dalton's atomic theory for a century. However, in the beginning of the 20th century, scientists like Sir J.J. Thomson, Lord Rutherford, and Niels Bohr came up with new findings, which revealed some drawbacks in Dalton's atomic theory. The drawbacks of Dalton's atomic theory are: it could explain the laws of chemical combination only by mass, but not by gaseous volumes. It could not explain why atoms of different elements have different masses and sizes. It could not explain how and why atoms of the different elements combine to form compounds. It failed to explain the nature of binding forces between the atoms and molecules, which accounts for the existence of the 3 states of matter: solid, liquid, and gaseous. And it makes no distinction between the ultimate particles of an element or a compound. So, they modified Dalton's atomic theory, and it is now known as the modern atomic theory. Here are the key findings of the theory. An atom is no longer considered indivisible. This means that an atom is a complex structure and is made up of electrons, protons, and neutrons. Atoms of the same element may have different atomic masses. Such atoms are known as isotopes. For example, a chlorine atom may have an atomic mass of 35 and 37. Atoms of different elements may have same atomic masses. Such atoms are known as isobars. For example, a calcium atom and an argon atom have the same atomic mass, that is, 40. From this, we can also conclude that atoms of different elements may be identical in one or more aspects. The ratio in which different atoms of different elements combine may be fixed and integral, but may not always be simple. For example, the elements C, H and O combine to form sugarcane. The ratio of the elements 12:22:11 is fixed and integral, but it's not a simple ratio. The atom is the smallest particle that takes part in a chemical reaction. In nuclear reactions, atoms of an element can be changed into another. For example, atoms of nitrogen can be changed to oxygen through bombardment of alpha rays.
On discovering that matter is made up of atoms, scientists' attention was shifted towards identifying the mass of atoms. Since atoms were small particles and could not be separated, scientists were not able to determine the actual mass of an atom by weighing it. It was possible to calculate the mass of an atom by weighing an element and then dividing the weight by the number of atoms. However, there was no method to count the number of atoms available in an element. In an attempt to find a solution to the problem in the 19th century, Dalton made some assumptions based on Gay-Lussac's findings. Based on Gay-Lussac's findings, Dalton assigned hydrogen a weight of 1. He used hydrogen as a standard for determining the atomic masses of other elements and published the first table of atomic masses. Note that the atomic masses in the table indicate relative mass and not the actual mass of the atoms, which means that the masses of elements is relative to the mass of hydrogen. In 1961, scientists met at the International Union of Pure and Applied Chemistry and decided to use carbon as the standard base. Carbon has 3 isotopes, C12, C13 and C14. Since C12 was found to be the most abundant, it was taken as the standard scale. By that time, due to the advancement of technology, scientists started using a mass spectrometer to calculate the accurate atomic mass of elements. The atomic mass of carbon was determined using a spectrometer and was found to be 12 atomic mass unit AMU. All other atoms were assigned a mass relative to the atomic mass unit of carbon. Thus, the atomic mass of an element is the number of times an atom of that element is heavier than an atom of carbon taken as 12. As carbon-12 is an isotope of carbon, it is represented as 12C. Therefore, one atomic mass unit is defined as a mass equal to 1/12 the mass of carbon-12 isotope. And the value of one atomic mass unit was determined to be 1.66056 multiplied by 10 raised to minus 24 gram. Let's determine the atomic mass unit of hydrogen based on this formula. We know that one atomic mass unit is equal to 1.66056 multiplied by 10 raised to minus 24 gram. The mass of a hydrogen atom was determined using a spectrometer and was found to be 1.6736 multiplied by 10 raised to minus 24 gram. Therefore, in terms of atomic mass unit, the mass of an atom of hydrogen atom is said to be 1.008 AMU. When chemists expressed atomic mass on carbon-12 scale, they named it as unified scale, and the unit was represented as U instead of AMU. Though AMU is still used in most places, chemists now use U as the unit. Hence, we can represent atomic mass of hydrogen as 1.008 or 1U, and that of oxygen as 15.9994 or 16U. We know that when atoms of the same elements possess different atomic masses, they are known as isotopes. Hence, for isotopes, the average value of the atomic masses is considered as the atomic mass unit. For example, chlorine has two isotopes with average atomic masses of 34.97 and 36.97 units respectively. The relative abundance of the isotopes is 0.755 and 0.245 respectively. Relative abundance refers to the abundance isotopes of an element, as naturally found on a planet. Average atomic mass of an isotope is the sum of abundance of each isotope multiplied by the precise atomic mass. Thus, the average atomic mass of chlorine is calculated as 35.46 U. Hence, the average atomic mass was redefined as the atomic mass of an element is the average relative mass of its atoms as compared with an atom of carbon-12 taken as 12U. We can also calculate the average atomic mass using fractional abundances of isotopes of an element. Fractional abundance of an isotope is the fraction of total number of atoms that is comprised of that particular isotope. The formula for calculating an average atomic mass from fractional abundance is fractional abundance multiplied by atomic mass of that fraction. Thus, the average atomic mass will be the sum of the products of fractional abundance of the isotopes and their corresponding mass numbers. For example, neon consists of three isotopes: neon 20, neon 21 and neon 22, which have mass numbers and fractional abundances as shown in the table. The average atomic mass of neon will be calculated 20.179 U. When the atomic mass of an element is expressed in grams, it is called gram atomic mass. Gram atomic mass is also called 1 gram atom of the element. For example, 1 gram of magnesium is equal to its atomic mass expressed in gram, which is 24 gram. Like atoms, molecules are also very small. Hence, their mass cannot be determined by weighing them. Therefore, the molecular mass is determined relative to the mass of carbon atom taken as 12U. The molecular mass of substance, element, or compound is the number of times the molecule of the substance is heavier than 1/12 the mass of an atom of carbon-12. In other words, we can say that the molecular mass of a substance is the average relative mass of its molecules, as compared with the mass of an atom of carbon-12 isotope taken as 12U. The molecular mass of any element or compound can be calculated by adding the atomic mass of all the atoms present in one molecule of that element or compound. For example, the molecular mass of water will be the atomic mass of 2 atoms of hydrogen plus the atomic mass of 1 atom of oxygen, which is 18.02U. When the molecular mass is expressed in grams, it is known as gram molecular mass. Gram molecular mass is also called 1 gram molecule of the substance. For example, 1 gram molecule of water is 18 grams. Lastly, let us look at ionic compounds. Ionic compounds such as sodium chloride or potassium nitrate do not contain discrete molecules as their constituent unit. The ions in such compounds are closely packed in a 3-dimensional structure. For example, in the sodium chloride crystal, an ionic bond is formed between a sodium ion and a chloride ion. However, in its crystalline form, each sodium ion is surrounded by 6 chloride ions. So, we have to calculate the formula mass instead of the molecular mass. Formula mass is the sum of atomic masses of atoms present in one formula unit. Thus, the formula mass of sodium chloride is the atomic mass of sodium plus the atomic mass of chlorine, which is 58.5U. When the formula mass is expressed in grams, it is known as gram formula mass. Before we begin, let's step into a store to buy some apples. Let's say we need 24 apples. When we collect them, we get them in 2 boxes, with 1 dozen or 12 apples in each box. Here, dozen is a unit of measurement that helps us simplify and state a large quantity, like 12. When scientists were working with elements and compounds, they felt the need to have a unit of measurement to count entities at the microscopic level. Thus, the SI base unit, mole, was introduced. Mole is the amount of substance which contains as many elementary entities as there are in 12 grams of carbon. Elementary entities may be atoms, molecules, ions, electrons, or protons. Note that 1 mole of a substance always contains the same number of entities, irrespective of the identity and kind of the substance. The term mole is used to count particles such as atoms, molecules, ions, electrons, and protons. Hence, we must indicate the nature of the particle under observation. For example, saying 1 mole of hydrogen would be incorrect. We need to specify the entity we are referring to. That is, hydrogen atoms or hydrogen molecules. Thus, the correct term would be 1 mole of hydrogen atoms or 1 mole of hydrogen molecules. But what is the value of a mole? Let's find out. We know that a carbon-12 atom is used as a base to calculate the atomic mass of elements. Hence, scientists used carbon as the base to determine the value of 1 mole. They used a mass spectrometer to determine the mass of a carbon-12 atom and found it to be 1.992648 multiplied by 10 raised to minus 23 gram. They then divided 12 gram moles of carbon-12 by the mass of carbon-12 and obtained 6.0221367 multiplied by 10 raised to 23, which is the number of atoms in 1 mole or 12 gram of carbon. This is the value of 1 mole and is known as Avogadro's number or Avogadro's constant, in the honor of Amedeo Avogadro, and is usually represented as Na. Avogadro's number or Avogadro's constant is defined as the number of elementary entities, atoms or molecules or ions in 1 mole of a substance. Thus, we can say that 1 mole of water molecules contains 6.022 multiplied by 10 raised to 23 water molecules. Having found the number of moles in a substance, we can determine the mass of a mole, also known as molar mass. Molar mass is the mass of 1 mole of substance expressed in grams. The molar mass is numerically equivalent to the atomic or molecular or formula mass in U. Let's determine the molar mass of water. We know that water comprises 2 hydrogen atoms and 1 oxygen atom. We can obtain the atomic masses of hydrogen and oxygen from the periodic table. The atomic mass of hydrogen is 1.00794 and the atomic mass of oxygen is 15.9994. If we add the atomic masses of 2 hydrogen atoms and 1 oxygen atom, we get the molar mass of water as 18.02 gram. We've learnt that molecular mass of a substance can be obtained by adding the atomic masses of all the atoms present in 1 molecule of the substance, and the molar mass is numerically equivalent to the atomic or molecular or formula mass in U. Thus, we can conclude that the mass of 1 mole of any substance is equal to its molecular mass. We have seen how to determine the number of entities present in a substance. At times, scientists also require to know the percentage of elements present in a compound. This information helps to determine the purity of the chemical compound under observation. The percentage composition of elements or constituent in a compound is the number of parts by mass of that element or constituent present in 100 parts by molar mass of the compound. Let's look at an example. We know that the molar mass of water is 18.02 grams. Based on this, we can calculate the percentage of hydrogen and oxygen as shown. Thus, the percentage of oxygen and hydrogen in water is 88.79 and 11.18 respectively. Molar mass and percentage composition helps us understand the quantitative data associated with a chemical compound. But how does one arrive at the chemical formula of a compound? In other words, how did scientists obtain the formula H2O? The chemical formula of a compound is derived from 2 parts, the empirical formula and the molecular formula. The empirical formula is defined as the formula which gives the simplest whole number ratio of the different atoms present in 1 molecule of the compound. For example, the empirical formula of water is H2O. This indicates that in water, 2 hydrogen atoms are present for each oxygen atom. Similarly, the empirical formula of glucose is CH2O. This indicates that there is 1 carbon atom for every 2 hydrogen and 1 oxygen atoms. Note that the empirical formula only indicates the atomic ratio of the elements present in one molecule of the compound. Now, let's look at molecular formula. The molecular formula is defined as the formula which gives the actual number of atoms of various elements present in one molecule of a compound. In case of water, the molecular formula is H2O, same as the empirical formula, because one molecule of water contains 2 atoms of hydrogen and 1 atom of oxygen. In case of glucose, the molecular formula is C6H12O6. This means that one molecule of glucose has 6 carbon atoms, 12 hydrogen atoms and 6 oxygen atoms. The molecular formula of a compound is an integral multiple of the empirical formula. The equation can be illustrated as shown. The value of N can be obtained by dividing the molecular mass with the empirical formula mass. The empirical formula mass is the sum of the atomic masses of the atoms present in the element. Let's say we have a compound CH2. The empirical formula of the compound will be the sum of the atomic masses of 1 carbon atom and 2 hydrogen atoms, which is 14 gram-mole. Now, let's say that we know the molecular mass of the compound is 28 gram-mole. Thus, 28 divided by 14 gives us 2. Then, we multiply 2 by the empirical formula and get C2H4. We've learnt how to calculate molar mass, percentage composition, empirical formula and molecular formula. But when do we apply these calculations in chemistry? Let's say we have conducted an experiment and obtained a compound that has 29.11% sodium, 40.51% sulfur, and 30.38% oxygen. And the molar mass of the compound is 158.1 gram. How can we determine the empirical and molecular formula of this compound? First, we have to convert the mass percent to gram. As we have the values in mass percent, we can consider the value of the sample as 100 gram and then convert the percent values to gram. Next, we have to determine the number of moles in each element. Divide the mass of element in gram with the atomic mass of the element. The atomic masses of various elements can be identified from the periodic table. Therefore, the relative atomic mass of sodium, sulfur, and oxygen are 23, 32.1, and 16 respectively. On substituting the values in the equation, we get the number of moles for each element as 1.266 and 1.897. Next, calculate the simplest molar ratio. Divide the moles of various elements present in the compound by the smallest quotient obtained as a result. This gives the simplest molar ratio as 1:1:1.5. If the ratios are not whole numbers, Then multiply the number with suitable integer to convert them into whole numbers. In this case, if we multiply all values by 2, we get all ratios as whole numbers. That is, 2:2:3. Write the empirical formula by mentioning the numbers after writing the symbols of respective elements. First, write the element symbols next to each other. Then, insert the obtained numerical value of the simplest whole number ratio at the lower right-hand corner of each symbol. This gives the empirical formula of the compound, that is, Na2S2O3. Now, let's see the steps to determine the molecular formula. First, calculate the empirical formula mass. The empirical formula mass can be obtained by adding the atomic masses of all the atoms present in the empirical formula, which is 158.1 gram. Now, divide the molar mass by the empirical formula mass to identify the value of N, which we get as 1. Then, molecular formula of a compound can be determined by multiplying empirical formula of the compound with N. In this case, the molecular formula will be the same as the empirical formula. That is, Na2S2O3. We know that chemical reactions can be illustrated through a chemical equation. A chemical equation can be divided into two parts. The reactants appear on the left side of the equation. In this reaction, hydrogen and oxygen are reactants. The products appear on the right side of the equation. In this example, water is the product. We've learnt that the law of conservation of mass states that in all chemical reactions, the total mass of the reactants is equal to the total mass of the products. This means that the equation of a chemical reaction should be balanced. Notice that the equation for water is balanced. The number of atoms on the left side is equal to the number of atoms on the right side. A chemical equation in which the number of atoms of each element is equal on the reactant side and the product side is called a balanced chemical equation. Let's look at the steps to balance a chemical equation. Let's say we have to write the balanced equation for the combustion of propane. The first step is to write the chemical formula for the reactants and products. In this case, propane, that is C3H8, reacts with dioxygen, O2, to form carbon dioxide, CO2, and water, H2O. Note that there are 3 carbon atoms, 8 hydrogen atoms, and 2 oxygen atoms on the left side, while there is 1 carbon atom, 2 hydrogen atoms, and 3 oxygen atoms on the right side. Next, we have to balance the number of atoms of each element one by one. Let's begin with carbon. There are 3 atoms on the left side and 1 atom on the right side. So, we will multiply CO2 by 3. This means that 3 carbon dioxide molecules will give us 3 carbon atoms. Now let's work on the hydrogen atoms. There are 8 atoms on the left side and 2 on the right side. So, we can multiply H2O by 4. This means that 4 molecules of water will give us 8 hydrogen atoms. Now, let's look at the oxygen atoms. there are 2 oxygen atoms on the left and 10 on the right side. 3 multiplied by 2 oxygen atoms, that is 6 oxygen atoms in carbon dioxide, and 4 multiplied by 1, that is 4 oxygen atoms in water. 6 plus 4 gives a total of 10 oxygen atoms on the right side. Hence, we will multiply O2 on the left side by 5. Finally, verify that the number of atoms in each element is balanced. In this case, we have equal number of atoms on both sides. Hence, this is a balanced chemical equation. A balanced equation helps determine the quantitative relationship between the reactants and products in terms of number of moles, molecules, atomic masses, and volumes. For example, according to this balanced chemical reaction, 1 molecule of propane gas reacts with 5 molecules of dioxygen gas to give 3 molecules of carbon dioxide and 4 molecules of water. And 1 mole of propane gas reacts with 5 moles of dioxygen gas to give 3 moles of carbon dioxide gas and 4 moles of water. Similarly, 44.09 atomic mass unit of propane gas reacts with 160 atomic mass unit of dioxygen to give 132.03 atomic mass unit of carbon dioxide and 72.06 atomic mass unit of water. And 44.09 gram of propane gas reacts with 160 gram of dioxygen to give 132.03 gram of carbon dioxide and 72.06 gram of water. And the total mass of the reactants, that is 204.9 grams, is equal to the total mass of the products, which is also 204.9 gram. The calculation of quantitative relationships of the reactants and products in a balanced chemical reaction is known as stoichiometry. The coefficients in a balanced chemical equation are called stoichiometric coefficients. Stoichiometric calculations help understand the mass and mass relationship. This means that if we know the mass of one of the reactants or products, we can determine the mass of the other reactants and products. Similarly, it helps understand mass and volume relationship. That is, if we know the mass or volume of one reactant or product, then we can calculate the mass or volume of the other reactants or products. And if we know the volume of one reactant or product, then we can calculate the volume of the other reactants or products. Most chemical reactions take place in solutions. Hence, we need to understand how to apply stoichiometry to reactions in solutions. For solutions, we need to know the concentration, that is, the number of moles present in a certain volume of solution. We can express the concentration of a solution present in a given volume through 4 methods. They are mass percent, mole fraction, molarity, and molality. Let's look at each method. The mass percent of a solution is determined by dividing the mass of the solute by the mass of the solution and multiplying it by 100. For example, let's say a solution is prepared by adding 4 grams of substance A to 20 grams of water. We need to find the mass percent of the solute. Based on the mass percent formula, we need to divide the mass of A by the mass of the solution. That is, mass of A plus the mass of water. After performing the mathematical calculation, we get the mass percent of A as 16.66. Now, let's look at mole fraction. Mole fraction is the ratio of number of moles of a particular component to the total number of moles of the solution. Mole fraction is a way to express the composition of mixture. For example, if a substance A dissolves in substance B, and their number of moles are Na and Nb respectively, then the mole fraction of A will be the number of moles of A divided by the number of moles of solution, and the mole fraction of B will be the number of moles of B divided by the number of moles of solution. Let's say we have to find the mole fractions of water and glycerol. When 92 gram glycerol is mixed with 90 gram water. Given that the molecular weight of water is 18 gram and the molecular weight of glycerol is 92 gram. To apply the mole fraction formula, we first need to find the number of moles in water and glycerol. The number of moles of water is 5 and the number of moles of glycerol is 1. We then add them to obtain the total number of moles in the solution. From the calculation, we get the total number of moles in the solution as 6. Then, we find the mole fraction as per the formula. We get the mole fraction of water as 0.833 and the mole fraction of glycerol as 0.167. Next, let's look at molarity. Molarity is the number of moles of solute in 1 liter of solution. It is represented as capital M. Let's say we have to find the molarity of a solution formed when water is added to 11 gram calcium chloride to make 100 ml of solution. To find the number of moles of a solute, we need to divide the mass of calcium chloride by the molar mass of calcium chloride and need to convert 100 milliliter solution into liter. By applying the formula for molarity, we get the molarity of the solutions as 1.0 m. Finally, let's look at molality. Molality is defined as the number of moles of a solute present in 1 kilogram of solvent, and it is denoted as lowercase m. Let's say we have to find the molality of a solution of 10 gram sodium hydroxide in 500 gram water. To find the number of moles of solute, we need to divide the mass of sodium hydroxide by the molar mass of sodium hydroxide. We also need to convert 500 gram water into kilogram. Thus, after applying the formula, we get the molality of the solution as 0.50 m. At times, when reactions occur, the reactants are not present in the amount required by the balanced chemical equation. Let's understand this concept through a real-life example. For example, let's say that 2 slices of bread and 1 slice of cheese makes 1 sandwich. Now, if we had a packet of bread with 10 slices and a packet of cheese with 6 slices, how many sandwiches can we make? The answer is 5 sandwiches. In this example, bread is present in lesser amount and gets fully consumed, and hence we cannot make any more sandwiches, although 1 slice of cheese is left. Thus, bread is known as a limiting reagent, as its shortfall prevents us from making any more sandwiches, while cheese is the reactant in excess. Let's look at the steps to find a limiting reagent and reactant in excess in a chemical reaction. Let's understand how to calculate limiting reagents from this example. Assume that we mix 50 kg of nitrogen gas and 10 kg of hydrogen gas to produce ammonia gas. Here, we have to determine the limiting reagent during the production of ammonia. First, we have to write the balanced chemical equation of the reaction. Next, we have to convert the given amount into moles. First, we'll convert the mass of nitrogen into grams, and then apply the formula to find the moles, which is 1785.7. Similarly, we'll convert the mass of hydrogen to gram, and then apply the formula. We get the moles of hydrogen as 4960.3. From the balanced chemical equation, we can conclude that 1 mole of nitrogen reacts with 3 moles of hydrogen. Thus, 1785.7 mole of nitrogen reacts with 5357.1 moles of hydrogen. However, we have 4960.3 moles of hydrogen, not 5357.1 moles. Thus, we can conclude that nitrogen is not the limiting agent. If we test in the reverse manner, that is, 3 moles of hydrogen reacts with 1 mole of nitrogen, we get 1653.4 moles of nitrogen, as against the 1785.7 moles of nitrogen. Thus, we can say that nitrogen is the excess reagent, while hydrogen is the limiting reagent.